A semiconductor is an insulator you can make conduct. So here's what I call the water analogy. So the voltage potential to move electrons from one atom to the next. These are the valence electrons. We have these so-called orbital, this happy family idea here. My chemistry teacher said that it's hard to break up a nuclear family. Once you have a full orbital shell, that doesn't want to change. If it's 4 valence electrons in that outer shell, it wants to stay there, so then it doesn't contribute the electrons. If you have an incomplete shell, those are available to conduct because they'll move. They're looking for a complete home. So what are these different things that we talk about every day? Voltage is the potential energy needed to move electrons from one atom to the next. Is that really true? Yeah, that's the mechanical model that actually happens. What about amperage? Amperage is the number of electrons that are flowing per second. That's current. It's like a river. It's the amount of water that's moving. What's resistance? It's the proportionality constant between these two. That varies by material. Some materials, you apply a little bit of incentive, they go. Sometimes electrons don't want to leave their atom. You have to put a lot of energy there. Those are the insulators. So semiconductors are primary insulators. Here's a cool thing. Once we know just this much chemistry, we can engineer this. So we're going to use silicon as our semiconductor, and then we're going to dope it with either boron or phosphorus. Now, back to our happy families. And this is the outer orbital. So we have 4 here. And guess what? I can add an additional electron if I have phosphorus sitting next to silicon. You see phosphorus has an additional electron relative to silicon. Boron is missing an electron. The number of valence electrons in silicon is balanced at 4. This has an extra electron. This has 1 less. So we take the silicon lattice. We then dope it with either boron or phosphorus. So since boron is group 3, it has 3 valence electrons. It has a deficit of 1 electron. We say that it's good for conducting holes. So actually what we're going to do is we're going to watch the movement of an electron go from atom to atom, leaving a hole behind. Okay, and you're going to say, what? So I think of it every day, actually, when I go at lunchtime or I move between parking lots at UCF. The carriers are the cars, and the lattice is the parking spaces. You can watch the car move as you're watching the electrons, you're watching current flow. Or you can see how the holes, which are the spaces left behind when people vacate the parking space, move. We use the same thing we call mobility of a carrier, actually. You'll take it in the semiconductor, and a lifetime of a hole. It's like how long in this lattice before an electron goes and occupies that spot. At UCF is probably the world's record for the limited lifetime for a hole in a parking lot. But I think of that every day, actually. Very good model. When you say doping, remember P and N type material? You may have heard those words. PN diode or PNP transistor, using these in a certain design. Let's take a look at this video. It puts it into motion.
Phosphorus has 5 outer electrons. A 5th phosphorus electron built into each.
So since he's sitting in a lattice that's supposed to have 4,
because of this structure,
that electron is not like have much loyalty to that phosphorus atom. You just put a little voltage, it's going to flow.
Atoms, on the other hand, have only 3 outer electrons.
He's sitting in a lattice of 4.
The silicon lattice, 1 silicon.
It's a hole waiting to get a car to come in. Park.
This creates electron holes. They move through the crystal like positively charged electricity particles.
But there is no positively charged. It's just the absence of a negative.
The transistors in modern memory chips are constructed from P and N conductive layers such as these. Transistors are the smallest control units in the microchips. In the heart of an NMOS transistor, for example, we find P and N conductive layers of silicon crystals. An additional layer consists of silicon oxide and acts as an insulator.
Okay, so before we make it too confused. So here we took the silicon lattice and they've doped these regions. Okay, there's different ways you can use diffusion, you can use ion implantation, but what they did is they exposed, they will etch with the photolithography, they'll expose these regions, then they'll implant. Okay, that can be just diffusion. It's in a high temperature and there's a little bit of phosphorus or boron. Interesting thing to me is the thing we use inside chips, the amazing things they do, they're not really like that exotic chemicals. They're not like rare earth elements, okay? Weird stuff. You know, boron and phosphorus are in your laundry detergent. How about ATP? If you're a biology person, what is it? Yeah, how I'm talking to you and how you're hearing me is ATP is working, right? There's phosphorus in us. It's making this electric conversion, right, for us, energy conversion. So what's happening here is we dope this with these different regions, okay? And there's some base and there's some well, okay? And then we're going to put this insulator in here. This insulator gives us what's called the field effect. So there's a couple different types of transistors. There's junction transistor and field effect transistor. Field effect, we say FET, and a junction transistor, the common is a bipolar junction transistor, is a common one. There's so many different types of field effect transistors. There's so many types of junction transistors. If you're an analog person and you want to amplify a signal, junction types are very good. They're good to make an amplifier in your guitar amplifier or your stereo in your car, but they're not so good at switching. These things are great for switching ones and zeros. And the reason is because this insulator has a super high insulating value. The resistance is enormous. You have to have a huge voltage to have any current flow through here. Silicon oxide is almost a perfect insulator. So what they're going to do now is they're going to have these two regions, and now here's the coolness. When a transistor switches, there's actually no current flow, or very, very little, okay, from the inputs to the output. Let's take a look.
A layer of electrically conductive polysilicon is applied on top of it.
Without this, we could not have computing the way we know it.
The middle one is attached to the gate, the electrically conductive polysilicon. If we apply an electrical charge only to the two outer connections, electricity is unable to flow. The transistor is blocked. Things are different when an additional charge is attached to the middle connection. The electrons from the P layer now wander toward the middle connection and accumulate at the border area between the silicon crystal and the insulation gate oxide.
So what's the point? So we built this structure out of silicon lattice. We've doped these two regions. And so the point is that there's excess carriers, in this case P-type excess carriers, in this substrate that are available to enter what we call the channel. The channel is between the two terminals, source and drain. This is the source and this is the drain. It's just like water. The water model is pretty good. Keep with the water model. This gate is a gate for the flow of current. They'll open the gate and they can flood the field. This is like this little bit of voltage, right, is potential energy. It doesn't actually flow into the channel, but what it does is it gets these guys to wake up and come out of their homes because they want to get this good positive energy. And guess what? They're available in the channel now to let the current flow. And that's how it works. The point is that since we don't actually have charge transfer between the input, we're going to make this an input to a gate, okay, a Boolean gate. We don't have a lot of energy wasted. So we can have billions of these on a chip and power from a battery. You know, try doing that with mechanical gears. It doesn't work.
The channel through which the electrons can flow is formed between the islands of N-conductive material. The electrical circuit is closed. The transistor can be switched back and forth between current off and current flow. That is to say, between 0 and 1.
Even cooler, it can be done picosecond order. All right. And it's going to lead us to Moore's law. What is a transistor? Once you learn the word, then everything's making sense. Transistor actually was crowdsourced by Bell Labs. Shockley tried for many years to make a working one. This is the world's first transistor. It was a display model. It's a contact or junction type. Okay, he made it big on purpose, and he actually made it to look like the symbol because he knew that this picture would be used a lot, and it's actually showing you the symbol. But it's another key thing to know. Every time you look at a schematic, pretty much the symbols always tell you what it's doing. These are helpful things because it saves time later, right? Here's a symbol for resistor. What's it mean? Okay, resistor, right? Well, the electrons are flowing through a wire. There's no resistance, but then they get here, they got a bumpy street, right? It's like you're going to make heat, right? What about a diode? It's only one way, and this is the direction that's shooting the current, right? And this is stop, right? So transistor is the same thing here. We're shooting current into this junction, but we have some terminals to modulate that, and that's where it gives us our switching or amplification effect. It's transferring resistance from the inputs, source and drain for us with FETs, into the channel. You're going to say, okay, so today transistors are very prolific. We make 10 to the 20 manufactured each year, so that's 10 billion for each of us on the planet. They're actually very simple. Electrons are the moving parts, and the cost is reduced down from a physics experiment in 1947. This is around 1962, mid-60s, okay, down to $5. You'd buy it in a little metal can, an individual transistor. We already talked about some of these. Now we build them with photolithography, 22 nanometers, 32 nanometers, 2014, 2015. Now we have 14 nanometer Broadwell. And to calibrate yourself, a human hair is 80,000 nanometers, so you can imagine how many transistors are in the width of a human hair. So the point is that reliability is an issue when we get to atomic dimensions. You can see here that this is a scanning electron microscope of Intel's process. They call it FinFET. So you can see here that these are only a few atoms wide, okay. And if you look up the silicon lattice, we're talking only 50 atoms wide here to make some of these structures. The transistor that we're using in our circuit is going to operate as a voltage-controlled switch. I'll show you the design for CMOS, storing a single bit using transistors and building some basic gate functions, just enough to start off on that, and you can take another class. So what we need to know for this class, because it's leading us to Moore's Law, which is our key point, we need to know so far in this module, which is the photolithography part, is the reason electronics becomes cheaper is really the photolithographic process decouples design complexity from production costs. Contrast that to 3D printing on a conventional 3D printer. 7-step fab process. You should know what these production processes are. We have a slide for that, right? We start with the silicon, molten silicon, build the ingot. You should know what the different steps of the fabrication process are, as identified in the slide. The concept behind engineering electron flow, right? That's what electronics is, right? Electronics is the engineering of electron flow. Electronics gets its name from electrons, okay? That's what we do. Geico. That's what we do. We make electrons flow or not flow. We need the materials people to help us do that. They make the transistor that allows us to engineer electron flow. Fabrication costs, it impacts chip costs and nonlinearity there in die size and defect rate. Physical view, here is a nice, probably if I had a single diagram of how a FET works, this is probably all you really need to know. If you're a computer engineer or above, or electrical engineer, you can take a course designing these. So here we have N-type dope substrate, and we put two P-wells here. One becomes source, one becomes drain. This red arrow is showing the path of current, okay, through here. But we can modulate the current flow by applying a voltage to this terminal. So we're switching, as we say, it's a voltage-controlled current switch. We're going to switch the current flow on and off by this voltage applied to this terminal. So this is like the input, right? And this is the output. If we connect a few of these together, the most classic one is the CMOS inverter. And we'll show a design for that soon. Yeah.
In this model,
yeah, good.
It comes up to fill the channel. Is that holes? It comes up.
Mr. Roper, yes. So what is this one? Your question is what's in here?
That's N-type, but when the channel forms, what is coming up there to fill the channel?
Okay, so great question. So if we dope this with N-type material, it has excess electrons. So those are the carriers, right? But what we're doing here is we're actually this is a whole. Dr. Yuan is an expert these, but there's a whole bunch of field effects that happen between here, and what this does, it makes a depletion region, so that we don't have current flow unless you have enough carriers that are there to bridge that gap. So what's the way to think about this? When you put these two side by side, they naturally, like, the carriers are going to deplete in this. It's beyond the scope. We make a moat around a castle, right? And to jump that moat, you need a lot of potential energy, kinetic energy, actually. So that's what's here, and then this is going to provide that, because the carriers will come out and they start to move, and once they start to move, then they're available to conduct. Once they come out of once they leave their their home orbital. They're just kind of moving around, and once they're moving around, then they don't notice that they're actually conducting and not what they actually came there for. Good questions. So actually, we apply a voltage to the gate. What's the difference between voltage and current? It's just like saying, what's the difference between flow rate of a, think back to a hose, right, of your garden hose, right, versus the pressure. Voltage is pressure. Voltage is potential energy. So we can have all different types of ratios of voltage and current. If people think this is silly, it totally works, and it's a good one. It's like, you know, you can have a little tiny garden hose at, you know, whatever, 100 psi before it explodes, but right, that's how we, pressure washer, right, we clean our wok, right? You don't use like gallon, you don't use a fire hose. Fire hose is high current and high voltage, right? But, you know, the pipe that goes to your house is, you know, fairly good current flow, but not too high voltage. So then what you do is you restrict it down, and you get a nozzle, right? That's thermodynamics class. And what happened? You jacked up the voltage, right? So here, what we're doing is we're applying a voltage here, but actually there's almost no current flow because of the blue, one of the world's best insulators. Because that lattice is perfect, and the silicon oxide, there's no carriers. So what happens is you make an electric field. But what's the classic example of electric field? So, so your question is the action of the gate terminal. It's a lot more like Van de Graaff generator and your hair. What was that about? Physics class, right? The best day of physics class was what? When you're in high school in physics, right? And you go in, there's a big, what's Van de Graaff generator, right? They still do that or not? They have to do it, right? Because it's the coolest thing. There's a big metal thing there, and it looks like a hair dryer, and yeah. So what's happening is actually it's putting an electric field, right? And then it's making your hair stand up, right? But actually there's no current flowing until you touch it and you get zapped, right? Then you get the current flow. So what we're doing here is we're putting an electric field into this channel, encouraging or discouraging the electrons to move. So no current flows in here, but that's the gate effect. Okay, so we want to show you enough because we're going to talk about Moore's law next. And that's technology scaling. We've seen transistors shrink, 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 and I've given you, I don't like history just for history, but enough to know like what's happening and why it's important is kind of a good, right? They give you some trends. This is during the Moore's era, okay, is that the increase in transistor count is about 60% per year. If we change that to time, right, and do 1/, that's twice, is doubling every 18 months to 2 years. Memory capacity is the same thing, but every 18 months to 2 years. Disk capacity, well, now we don't even use disks anymore. We use SSDs because these got so large. Don't need mechanical disk anymore, electromechanical. But we see a reduction in chip price. Okay, so what the point is, if your customer wants you to bid a project, what do you expect? It's a 5-year maintenance or something. You have to update the computers every so many years and put new ones there. You want to be profitable. What are you expecting to pay? And the customer says, I need this many gigabytes. What's going to happen to the price? Okay. Every 18 months to 2 years, we expect a doubling of capacity for the same cost. What's that mean? Same wafer manufacturing process, photolithography, but we've got twice as many bytes per chip. That's called technology scaling. This process, we keep reducing the feature size. Here's historical feature sizes, okay, and we're down in here now. And you get to, I think it's going to run out. People always ask, when do you think it's going to run out? From reading these papers and talking to people at conferences and stuff, Intel is really, they're probably a generation ahead of everybody. The NAND, you can do 10 nanometer NAND flash, but it's a very simple process. It's not good for building data paths and so forth. Intel is probably at least one process generation ahead. The people there think 10 nanometer will probably work, and 5 is pretty iffy, okay? And if you look at 5 nanometers, that's just 18 atomic distances. So probably cannot scale much more and get a transistor effect. Have a channel, right, where you're encouraging, you know, once the parking lot gets too small, you know, you can't have holes in electrons anymore because you don't have this transistor effect. We call these process technology nodes, is the size, right, of the feature. They call it half pitch. They measure it different ways, and sometimes it's like unemployment numbers from the government. They kind of play with them, right? Underemployed, unemployed. So they're going to say, you know, is this 14 nanometers the half pitch, or is this the channel width? Different manufacturers change, but this is the general trend, okay? So why do you want to familiarize yourself with at least this region of this? Because when you buy a product, the nanometers is not arguable, okay? It's objective. Everybody's going to say this is the best chip in the world. It has the fastest this and the best that, and they can't play with this. So this is telling you that you're getting the newest technology when you buy something that's at the leading edge here. So for example, Broadwell is 14 nanometer in your notebook. That's amazing. When I started as a graduate student, we were around here, and you know, I'll never forget the first day of class. I did a master's in electrical, and I did semiconductor emphasis. And the professor's pounding on the desk and say, you know, people are writing these papers about submicron design, and said, well, you know, I think because of wavelength of light, we cannot go below 560 nanometers. You cannot do it. And he said, well, here we are, right? So a lot of times when people say you can't do something, like I said earlier in the lecture, right? But we are getting to atomic scale, so to have a transistor effect is getting a little more difficult. Now we can do switching with magnetic properties of single electrons, the spintronics, something my lab works on, and so forth. So there's things we can do, but they're not the easy thing, okay? And not the thing that we got good at, right? And it took 20 years to get good at this. Try some more examples here. We have a graphic that's showing you this time progression. So if you work, you may get hired different phases, right? So there's production, development, and research, okay? Let's say you have a bachelor's degree, you're here. A master's degree, you're probably here. A PhD, you're looking at new designs. Here's Moore's law on a graph, and you'll see this graph many times, many books, many ways. But if you plot as long as ICs were made, integrated circuits, it's almost linear on a log scale here. So this is the 4004, had 2,300 transistors, and then we got 10,000, 68,000, there you go, 68,000 transistors here, and going up now we're several billion transistors. So the point is that we're doubling at a constant rate. Again, anytime you have a graph where this is time here and this is log and it's a straight line, you're doubling at a constant rate. That number of transistors per chip and die. What's the difference between chip and die? A die is in the chip. It's an unpackaged chip. Moore's law is the number of transistors per chip doubles. What about memory capacity? Memory capacity, since it's based on transistors, we have a module to show you that. We're going to look inside of a memory cell and show you the transistors. Moore's law does apply to dynamic RAM capacity, which is main memory. So dynamic RAM is main memory, so main memory does apply with Moore's law. It's almost a straight line on a log scale. What about CPU speed and memory speed? And even you guys have seen that we don't double every year, 18 months or so on CPU speed. It goes up, but at a much more gradual rate. And they had a few different phases here. This was increasing a lot. In the 90s, it was really incredible. I was working with 25 megahertz. By the time I finished my project, it was 40 megahertz, and then 100 megahertz, and it's like every 6 months, new PCs would come out, or new chips, and they would just double the speed of what you had just 6 months ago for the same price. It was really outrageous, actually. And then what happened, the chips started to get too hot, and then we had to slow down, and we'll talk about that, because we need you to design new ways to help with that. So if we look at the aggregate of these effects, this is processor performance. We said measuring performance is difficult. Take execution time for a benchmark and look at the percent of time spent on processor-intensive instructions, ALU logic, versus load store, which is data transfer. Memory has not improved at the same rate that the processor speed has improved. Why? Because it turns out storing a bit is a hard thing to do. It's counterintuitive. Making a full adder seems more difficult than remembering if a bit's a 1 or a 0. But remember, if a bit's a 1 or 0, we haven't come up with any breakthrough ideas how to do that. We'll show you a few different designs. Either you put two inverters back to back, Do you guys do that in 3342 and you watch the 1010? That's a static RAM design. Or you can use a capacitor and store 1 or 0. That's what we do here. But it turns out we can't scale it very well, okay? So we're looking for new ideas, bright ideas. So when will Moore's Law end? I think it will likely continue up through 10 nanometer and maybe a little bit further in some applications. But the point is, continue in a straight line, we have a single atom per transistor. We know a transistor effect is not possible with a single atom. You have to have your band gap, you have to have a depletion region, you have to have a channel. We need at least 10 atoms to do that. So who cares? Well, we're so used to in society that electronics gets cheaper every year and more functionality and more jobs because there's more things for us to do, because now we can do things that used to fill a whole room in your pocket. People want to hire you because there's money to be made to do that. So what's going to be the focus, because Moore's Law is ending? We have post-CMOS options. Spintronics is something I'm interested in. You can actually buy a Spintronics chip for memory. But some of these, like the quantum dot and so forth, you need to operate cryogenic quantum cellular automata, 512 qubits. 512 quantum bits. So you have 512 bits total in the whole machine to store everything. It's still physics, so we're going to get there. We try these different techniques and make them better, just like when people want to invent transistor. Before the 20 years happens, what is there to do? Well, the good news, there's a lot of cool things. Low power, low energy, making things reliable, adaptive and evolvable hardware, having hardware that can adapt to its environment. This is very interesting to me. NASA funds my research. Say you have a satellite, they have over 100 FPGA chips on board. You can't have a spare for each one, and you can't go up there and fix it when it fails, so what do? Well, since it's reconfigurable, it's a field programmable gate array, we can actually allow it to rewire itself to the conditions. Wearable computing, all kinds of cool things here. So I'll let you click on these on your own time. Here's an IoT video. Another video? All right. Okay, so twist your arm. All right. So people always ask, what's this Internet of Things?
Physical objects have always generated an enormous amount of data, but we didn't used to be able to hear it, to see it, to capture it. Now we can, because all of this stuff is now instrumented.
That's a huge change in the world from even 15 years ago.
So in effect, cloud has grown essentially our system.
There's more things on the internet than there are people on the internet. That's really what we mean by the Internet of Things. Then you get this sea of data that you just drown in, literally.
Called big data.
It's been quite well documented in the DIKW triangle of data, information, knowledge, and the top is wisdom. The D at the bottom is a sea of data, and when we get this data back home and start doing stuff with it, we apply intelligence to it and transform up that stack. So we go from data into information, information into knowledge, and then glean some wisdom from that. Smart Planet story is all about. But the ideal day, I guess, would be that I wake up in the morning and my alarm clock went up at the right time because it had looked in my diary to know when my
Actually, we're kind of here.
ferry I need to get, and therefore what time I need to get up. The bathroom heater would have been on for half an hour before that time to make the bathroom.
If you have a Nest in your Google in your house, thermostat
overnight, and therefore that my ice was going to need to be scraped off my car, so I need to leave the house 5 minutes earlier. And then I'd be getting a notification, perhaps an audio announcement in my car as I drive to the ferry saying, "Oh, the ferries are running 5 minutes late, so no need to."
How many people use Waze?
All that stuff is being handled by
awesome, right?
autonomic systems of little agents looking out on my behalf for the things it knows I want to do.
Waze.
Just making me aware of what's going on, so I can plan my day accordingly.
What's that?
So the system of systems is really converged when you start to link these things.
Because they're
So
checking it or
you've
what?
got isolated systems during the water.
I'm a passive listener.
Checking if the windows and doors are open, that kind of stuff. It's a system, certainly, but it's not a system of systems. But if you start to think about the power grid, first of all, the appliances negotiate with each other. So they say, okay, guys, Andy wants all 3 of us to operate, but it's going to be bad for the grid if we all go on at the same time. So now suddenly we've got systems talking to each other, so acting smarter because they know about each other, which overall makes the entire system more efficient.
Duke Energy, if you own a house or if you, I don't know if you guys in apartments, they send you this stuff too, but they want to go and put a box on your refrigerator, and they're not that smart actually. They just shut it off for a few hours at peak times during the day, and they use the cold capacitance inside your fridge to hopefully things don't spoil, but this way it saves them from building a new power plant. So Internet of Things is, I think, a big hiring area for every discipline, because we need to design very cheap, very energy efficient. Maybe these things even use ambient energy from Wi-Fi signals, and you can do this at a very, very small update rate. Okay, not megahertz, but kilohertz. You can make a processor that runs off of just ambient energy if it's very, very efficient. So, what is energy consumption and performance if you wanted to do something like that? Here's some metrics. I mentioned this pretty well, and here's an example. Different processors have different energy profiles as well as throughput profiles. So here's frequency as the clock rate, the same, but you can see that this is a much higher MIPS per milliwatt. So this is the number of instructions, millions, per second, divided by the number of milliwatts is the heat dissipated by that chip. For every milliwatt of energy dissipated, this is doing a lot more work, potentially, if the software can take advantage of it. We're going to give you an equation to calculate that. An example, energy efficiency is an important metric for mobile devices and data centers. Energy efficiency turns out to be processor throughput, as I just mentioned here, divided by the energy consumed. Videos. This is a very cool one.
By the turn of the millennium, experts said that tiny chips,
This is why we went to multi-core.
hundreds of millions of transistors,
Mr. Gray asked me what year,
much cheaper.
turn of the century.
Scientists at Intel a microprocessor to do more.
Well, the Core i7 is a pretty radical redesign. In fact, it's one of the biggest changes in the way the PC works in quite a while. So the things we've done are kind of open it up so that it can be fed, so open the processor up so that you can feed it with data better.
Intel did this with a number of innovations, such as moving the memory controller onto the chip to achieve higher memory bandwidth, turbo boost technology, which increases frequency when the
Clock rate.
detects it has available power headroom, and an integrated power gate.
What's power headroom? It sounds like some new Monster headphones or something. What's power headroom? So we said here that we have power that's dissipated by the chip. Power equates to cooling need. If you have power headroom, means the chip is not overheated yet. You can make it a little bit hotter before it breaks. So what they're going to do here is they're going to change the frequency. So when it starts to get too hot, they slow it down, it then cools down, then you got power headroom, you've made some space, you can jack the frequency back up, or voltage.
Soft power to those cores which aren't in use.
And we can smooth between cores. That's the cool part.
Like Intel fellow Glenn Hinton, saying the technologies increase performance and energy efficiency.
The guys from Power Management team did a lot of work to reduce the overall and actively manage the power so that if one core is running, we get a lot of power to that, so it's running really high performance, that's turbo mode, and if all the cores are working, we adjust the frequency and voltage to make everything work well. And so that whole very active power management went way beyond anything we've done on any of our previous chips.
At Intel's lab in Silicon,
If you ask me, Intel is still the leader on that. They've got a really good job.
software configuration,
Core level coordination.
especially in high-end gaming.
I manage a group of guys that our job is to look at the products that Intel's going to be producing and try to explain the benefits in terms that people can understand, that they can relate to things they really do with the PC. So instead of just talking about this thing's...
That's his job title.
We try to find ways to say, oh, so what Regina is doing here...
See, some motivation for graduate school.
...release, and she'll try out...
Performance engineer.
...settings, whether it's screen resolution or the quality settings in the game. So whenever new games launch, she has to spend just hours in here. It's a terrible job. Going and playing it over and over and over again until she comes up with the right settings. It's hard. And the right test.
Francois Pied-Noel is testing the Core i7 here on an Intel motherboard. So far, he's observed bandwidth that is 2 times higher than on a previous quad-core.
Relative performance, a lot of things we talked about. Bandwidth we talked about. Throughput.
Where the power here or here. It's a ping pong between architecture team, and I'm sitting in the middle.
It's a heck of a heat sink.
Right hand, the left hand, the hand, and we got a lot of people in the team.
This is the lab where we're doing a lot of the functional validation of the handle, making sure that it's a good, robust.
So what's functional validation? I try to introduce these terms. So we go to job interview and so they say do functional validation. What is he talking about? Is he talking about the band gap of the semiconductor? No, he's saying does the input and output transformation, that's the function, right? Does the full adder work? Does the multiplier work? That's functional validation. We have performance, we have function, energy.
Consumers. We also check our performance in labs just like this up here in Oregon. As we have our
See, function, we also test the performance. After the function works, then you make it efficient. Part B of the lab this week, make it efficient.
Involve thousands of engineers in places such as Oregon, California, and Arizona, and in Malaysia and Costa Rica. Ronnie Borka oversaw the development of the microprocessor across Intel's many organizations, handling tasks like architecture and design, manufacturing, testing, and development.
These are great jobs, cool stuff.
And over time,
If you can get into Intel internship,
structures better and
take it.
better so that it really progresses very seamlessly. Because the timelines, one thing which is constant is the timeline when you're going to deliver and what you said you would deliver.
Who set that timeline? What is a timeline? Give me some units on the Gantt chart, right? What you said Gantt chart was a timeline, right? Every 18 months to 2 years, right? Which was Moore's law. Okay, so that's what this is. ITRS was International Technology Roadmap for Semiconductors. We had the slide. It's a consortium of companies that says 2 years from now we're going to go from 28 nanometer to 22 nanometer process. So that means if you're a tool maker, which you're making the whatever it is, oven, the scanning electron microscope, it needs to accommodate that diffusion rate so they can plan ahead because everybody gets on the same page. Intel has its own internal process called tick-tock.
Intel delivers chips on its tick-tock model. The tick represents advances in process technology, such as from 65 nanometer to 40.
That's device technology.
In 2007. The tock is a new microarchitecture, in this case, the handle.
With a TOG processor, we get the chance to overhaul complete microarchitecture as well as the platform. The internal core has been changed significantly for added performance as well as for better energy efficiency.
Let's take a look at the trend. We talked about a couple trends, right? Is Moore's law is the first trend. Moore's law, looking at the number of transistors per chip and the doubling every 2 years or so. Because of Moore's law, and we were adding more and more transistors per chip, if you look at historically what happened, we hit something called a power wall. And this was discussed in the video. Jeffrey Hinton, Dr. Hinton from Intel Research Labs, mentioned that when they got around 2003 or so, they started to say, if we're looking ahead in the future, we're going to have a problem on the chip that's going to overheat. We're going to be able to build this number of transistors, we hope. Won't be able to cool it. So one way to deal with this issue, which we call the power wall, we got to 130 watts total power dissipation on the chip. So to cool it, what we're going to do is have multiple cores, and we keep them active at different times. He also mentioned in the video about changing the voltage, changing the frequency when we have what he called power headroom. Power headroom was when we had additional space in the power budget before it overheats. So here's a graph of, this is clock rate versus time, and the power in watts is black, blue clock rates. This is in megahertz. What is the underlying equation causing this effect when we see this greater than linear increase in power? The idea is that power is capacitance times voltage squared times frequency. So the equation that, the way I remember it, is this, just the letters P equals C V squared F. But the key term here is voltage squared. So if you want to reduce power, the longest lever you have is to reduce voltage. If we can cut the voltage in half, you've reduced the power by a factor of 4. What's the relation between power and frequency is 1 to 1. So if you look over this period of time, from the 286 up to present, we've had the voltage decrease from 5 volts to 1 volt. 5 volts is TTL, stands for transistor logic. A lot of interfacing circuits still use TTL signaling. We call signaling is what's a 1 and what's a 0. So logic 1, a true, in this case is 5 volts, right? And then false is always 0 volts. For positive logic, you can have negative logic too. But in any case, TTL signaling 5 volts, we kept reducing the voltage by a better circuit design. And now we're around in the 1 volt, even 0.8 volt. And the frequency output went up by a factor of 1,000. So instead of having 3 megahertz, now we have 3 gigahertz. So I already mentioned this one. What's the effect of cutting the voltage in half? It's going to be a factor of 4. About cutting the frequency in half. Intel said the chip's getting too hot, so we reduced the frequency. So suppose I cut the frequency in half, what happens to the power dissipation? Yeah, that's in half, it's proportional. What about 10% less capacitance? Yeah, you're going to reduce 10% the power dissipation. So let's try a problem. So this is pretty realistic. So you're in the design meeting and someone's giving some parameters and you have to say where we're going to be as far as how many transistors you can put on this die and before it overheats, and they give you a power budget. So 85% of capacitive load that's coming from the transistor design department has a better design for the transistor. I'm going to reduce the voltage by 15% and reduce the frequency by 15%. One way you can reduce the frequency by 15% without the performance hit would be to use a wider data bus. And we're not doing as many instructions per second, but each instruction is crunching more bits, or a more powerful instruction set. So someone asks, how does this power dissipation compare with the original design? Prepare a precise declarative statement. So we use the P equals C V squared F equation almost directly, but these are ratios because we're reducing this. So we don't know what the old capacitance was, but we know that the new one is 85% of that, right? Because it's reduced 15. And then the new voltage is 85% of the old voltage and so forth. It turns out whatever the old values were cancel. And you have 0.85 to the 4th power, because these are all 15s or 85s. It's just a coincidence in this problem to make it easy to calculate. And it comes out to be 0.52. So what does that number mean? Exactly. So that's your declarative statement. So the declarative statement, cut the power dissipation by nearly half. What do you think? Okay. So we talked what the power wall is, and this led us to multiple cores. Multiple cores allow increase in performance at the same frequency without having this issue of running against the power wall necessarily. And we've talked about Amdahl's law, where it gives us a limiting behavior for how much benefit we can have from multiple cores. So optimization and communication, this is something that we hadn't talked about. This is really a future class, this computer architecture class. In the ideal case is Amdahl's law that communication synchronization was 0. You know, when you invite friends over to your house to help you move, start playing volleyball with them, which always happens, right? Or frisbee. Or they have to eat pizza, right? That's overhead. You have additional cores to get some work done, but they have to communicate. What's a partial result? From one core has to communicate with the partial result of another. That's communication and synchronization overhead. And again, not all cores are active simultaneously. So this is a little bit downside, but the good side for the power wall, this allows thermal smoothing. We can move a process from one, or a thread, from one core to another core if that core is getting too hot. We can move it around. So that was the idea of multiple cores and power wall, but how does power relate to energy? Energy and power are related, but they're two different distinct physical quantities. Energy is measured in units of joules, as you know from physics. We can calculate the number of joules needed to complete a workload. I put that in as part 2 of your project. In the lab, you're actually going to calculate the number of joules required for your design. And I'm going to ask you to try to minimize that. Something that can fit into a couple hours' time that really relates to Yahoo or Amazon would hire you to do in their data center. So on the data center end, that corresponds to the entire workload, but if you're on a mobile device, Internet of Things, that corresponds to battery life. How's that differ from power? Power relates to the basically cooling needs of the CPU, the size of the heat sink. The relation between these is units of watt for power, but the relation is energy is power times time. In the case of computing, it's the running time of the process. Or if it's just the processor, it's the execution time. So this is kind of coolness here, okay? If we do a really good job on the energy of our design, you could run a dual-core Intel Pentium off of a solar cell. We can find the video on the web, but this was the Intel Developers Forum, IDF. If you want to see something cool every year, go to the video. It's actually the new one's just out. I haven't got a chance to watch it yet. What they did here is they used basically a potato battery. What's a potato battery? Yeah, use potato as battery. Good. And how do you build it? Yeah, they put some metal. So they usually use some zinc and some copper, and then they donate ion, so you get some electron flow. And then coolness here, they did this. This is basically a potato battery, so they have the electrodes here, and they got enough to run on this Pentium processor. This is a 32 nanometer. Can even do better now. This is a couple years ago. Off of a glass of wine, so it doesn't need a battery even. And they drew the fractal image. This is a wine-powered processor. And so what's the coolness in this? So the coolness is only 2 milliwatts. The whole processor's 2 milliwatt. And the operating voltage, remember we were 5 volts? Now we're 280 millivolts. How much of a volt is that? 0.2. 8, huh? 0.2. But here's the catch. What happened to F? Yeah, 3 megahertz instead of 3 gigahertz. So actually what they do is they have this sliding scale, and he talked about his turbo boost, Dr. Hinton, in the video. So Intel has done a really good job with this. All their parts, all their devices are made to work at this adjustable frequency in a large range, and they drop this voltage down, he dropped the frequency down, but maybe this is an Internet of Things. It doesn't need to be running too fast. Power relate to energy and performance. I found this graph really shows it. This is the governing equation, as I mentioned. If this is continuous quantity, you can use integral instead of multiply. They're the same thing. This is where do we get integral from? Newton and the calculus. In the old days, the integral used to be written more like this. It's a sum, actually. It was the letter S for sum. So we're actually summing up all these little So which the processor below has a lower peak power dissipation? These are continuous waveforms, so we would use this equation, but just eyeballing the graph, we have 2 processors. This is what? This is the workload versus time. For AMD's power dissipation, so we're looking at it as the power dissipation over time as we run the workload. When we start it, there's not too much to do. We're initializing. Then we're crunching some data. And then here we get pretty busy. It goes up and down. And then here's the graph for MIPS on the same workload over time. This is power versus time. So which processor below has a lower energy consumption? What do you think? Yeah, and why? You're right. Yes. Yes, why? It is the integral. So integral is the area under the curve. So if I look here, that even though this has a higher power dissipation, in this case peak power, I see the peaks of this graph are higher. I mean, I need a bigger cooling capability, a bigger heat sink on the MIPS. Which battery will last longer? MIPS. All right. Okay. So if I don't want the chip to get damaged, I have to have a cooling capability that's sufficient enough for the peak dissipation of power. But if I look at the area under the curve, I get to the end of this, which drained the battery more, the AMD is actually draining the battery more. Key idea is energy and power are 2 related but different physical quantities. Energy relates to battery life. Power relates to the size of the heat sink. So what we just said is lower